Hello chemists, here we have a question under chemical equilibrium. So the guiding question says sulfur dioxide reacts with oxygen gas to produce sulfur trioxide. At equilibrium, the partial pressures of each gas were found to be 0.10 atmospheres and 0.30 atmospheres and 0.45 atmospheres for sulfur dioxide, oxygen, and sulfur trioxide, respectively. Calculate the equilibrium constant Kp. If Kc, or equilibrium constant in terms of concentration for the reaction shown below, is 9.60 at 300 degrees Celsius, what is the value of Kp at this temperature? If Kp is equal to 1.45 times 10 to the power negative 3 at 500 degrees Celsius, what is the value of Kc at this temperature? So this is the problem that has been given to us. Now let's write down the chemical equation, and then this is going to guide us in how we are going to answer this problem. So we have that sulfur dioxide gas reacts with oxygen. This is a reversible reaction giving us sulfur trioxide. This reaction is very important in the production of sulfuric acid, what we call the contact process. Let's do the balancing of this chemical equation and we see. So if we put a 2 here, oxygen becomes 6, sulfur becomes 2, and when we put a 2 here, also oxygen gets balanced and sulfur balanced, so the whole equation is balanced. Let's calculate the equilibrium constant Kp. So according to this reaction, applying law of mass action, you'll find that Kp, which is equal to the partial pressures of the products divided by the partial pressures of the reactants raised to their stoichiometric exponents or constants. So here, the partial pressure of sulfur trioxide, we don't know it, but we are going to raise it with a power of 2. Divided it by the partial pressure of sulfur dioxide raised to a power of 2 times the partial pressure of oxygen raised to a power of 1. So we are told that the partial pressure of sulfur trioxide is 0.45, the other one for sulfur dioxide is 0.1, and for oxygen is 0.3. So we just substitute in those values, 0.45 squared divided by 0.1 squared times 0.3 power 1. And using my calculator, I find that I have 67.5. So Kp is 67.5. Now, we are told that Kc for the reaction is 9.6 at 300 degrees Celsius. What is the value of Kp at this temperature? So now, let's consider first of all, consider a reaction. Of course, it is what we are going to generate here is a general expression that is going to help us answer the above question. So we have A, probably, that has A, okay, plus B, giving us C and D. So we are going to add the stoichiometric factors. So here we have B, here we have C, here we have D. So that means Kp for this is going to be the partial pressure of A, power A, the partial pressure of D. Usually it has to be products out of reactant. So this is going to be partial pressure of C, power C, times partial pressure of D, power D, divided by the partial pressure of A, power A, times the partial pressure of B, power B. But according to ideal gas equation, we know that PV is equal to nRT, whereby R is the universal gas constant, T is temperature, N is the number of moles, V is volume, P is pressure. Meaning that P is going to be N out of V, then RT, which is equal to concentration times RT. Why are we calling it concentration? Because we know that the concentration that we are always given is in terms of moles per unit volume. So we always have the number of moles divided by volume. So that's why we are saying this is the same as concentration times RT. So meaning, if I have this equation, I can now substitute for each component, like C, D, A, B, you can substitute it by its partial pressure based on this simplification. Kp will therefore equal to, this is going to be the concentration of C times RT power C times the concentration of D times RT power D divided by the concentration of A power, okay, times, obviously we are multiplying it by RT also, times RT power A times the concentration of B times RT power B. And this is going to be the concentration of C power C, okay, times the concentration of D power D times RT, okay. Since this RT and that RT are the same, we shall raise them to the power of C plus D. Obviously, if I'm applying the laws of indices, where I have the same bases like A power maybe J times A power K. This is the same as A power J plus K. So this is what I'm applying here. So RT to power C plus D. Likewise, what is going to be down here will be the concentration of A to power A times the concentration of B to power B, then times RT to power also A plus B. Kp will therefore equal to what? Kp is going to equal to the concentration of C, okay, power C, times the concentration of D, power D, divided by the concentration of A, power A, and concentration of B, power B, then times RT, which is going to be C plus D, okay, divided by RT A plus B. But this component here is what we call Kc. This is the equilibrium constant in terms of concentration. So I will say that Kp will equal to Kc times RT. If again I apply the rules of indices, I'll have C plus D minus A plus B. So if I let change in moles to equal to C plus D minus A plus B, then that means our Kp will equal to Kc times RT to power the change in number of moles. So from here, we already know we know Kc, so we can substitute in for R and T, and then we shall be good to go. So we already know that Kc is equal to 9.6, and the temperatures are 300 degrees Celsius, and this is the same as 300 plus 273, giving us 573 Kelvin. So what about R? R is the universal gas constant, and we can it as 8.3145 in terms of joules per mole per Kelvin, but we also have the same R equivalent to 0.08206 liters, okay, atmospheres per mole per Kelvin. So since we have the partial pressures always in terms of atmospheres, we are going to use this R. So what does that mean? I'm going to have Kp. So once we have that, we are going to substitute in our equation here. So that Kp will equal to Kc, which is 9.6. Then we multiply by 0.08206. Then we are multiplying it by temperature 573, and everything to power the change in N. But the change in N is equal to, remember, according to the reaction that we have here, we have this as, we will be getting the products, that is 2, okay? We take away the sum of moles of the reactants. So this is going to be 2 plus 1, which gives us 2 minus 3, and this is negative 1. So this is the change number of moles, and that's what we are going to use here. This is 2 minus 3, giving us negative 1. So Kp will equal to 9.6 times 0.08206 times 573 power negative 1. So my Kp is equal to 0.2042. The next question is that if Kp is equal to 1.45 times 10 to the power negative 3 at 500 degrees Celsius, what is the value of Kc at this temperature? So that means I'll be looking for Kc, which is equal to Kp divided by RT power, the change in N. And this is going to be, Kp is given as 1.45 times 10 power negative 3 divided by 0.08206 times, this is going to be 500 plus 273, and this is to power negative 1. So the Kc value is going to be 1.45 times 10 power negative 3. We are dividing it by, remember, you have a bracket here. And this is giving us, this is 0.08206 times 500 plus 273, and this is power negative 1. This is giving us 0.092. So that becomes our Kc value when the Kp value becomes 1.45 exponent negative 3 at a temperature of 500 degrees Celsius.